I'm going to have a look at this quite difficult forces question from the November 2014 paper. The first question tells you that force is a vector quantity. First thing you're thinking is what's vector? Remember, a vector is something with size or magnitude and direction. It's asking you to state 3 other vector quantities. So this is anything that can have a size and a direction. So things like displacement, velocity, quite an easy one to remember, VV, velocity vector. Other ones you could have are acceleration, momentum, weight, which is a type of force, so perhaps a bit risky to have, but those would be my top 4 to go for, because remember you can't use force because it's there. Question B, the question's there. You can pause and read that if you'd like to. Now, while I'm reading this, it's a good idea to point out some really key points. It tells you that the magnitude and direction, so direction, that's that angle here. So this is the direction, so theta, are adjusted so the object remains in equilibrium, and that's probably key here. And I guess the question is going to be all about that. How can this remain in equilibrium when z and x have a force? Well, if you think about it, if we did a sort of vector triangle, here's force z, here's force x, and we can see that as long as y closes that gap, remember if we have a closed vector triangle, we have no resultant force, and that means that the object is in equilibrium. So y is going to have to adjust its angle and its size to keep this triangle closed. For example, if x gets bigger all of a sudden to here, we can see that our new y would be at a smaller angle but have a larger magnitude. And remember, this is this idea of a vector, so that it has size and direction. In this case, the direction is the angle from the horizontal. We've got a nice juicy little graph here, which is showing the size of x and y and how they are related. The first question asks you to use figure 3.2 to estimate the magnitude of y for x is 0. Now, normally it would just be a joy to dot up with x is 0 and see where it intercepts, but they haven't finished the line for us. So we're just looking for what sort of pattern is this showing. Well, it's quite clear that this is beginning to tail out. If we kind of continue it, we can see that it's going to flatten out approximately at 70. In this exam, they'll allow probably a newton either side, because obviously it depends on kind of where you've estimated that line is going to go. It tells you you're using figure 3.2 to estimate this, so that suggests there's no calculation. We're just using the graph to do this, and hopefully we can get it off that graph. State and explain the value of theta, the angle, for x is 0. So, we're saying that x is 0. Right, if we look here, that's telling us that this vector, x, is equal to 0, so it does not exist. So basically left with this, the z vector, and y at some angle theta. Now very quickly you need to see that this needs to be in equilibrium, so it's always worth drawing this out and trying to work out, and it's quite clear that if z is directly downwards, y is going to have to be in the opposite direction and equal in size. So y is going to have to equal z in terms of size, but be opposite in direction. What angle is that? Well, the angle, as you can see in the diagram, is measured relative to the horizontal. So we can see that that angle is going to be 90 degrees. You could also do this by knowing that obviously z is 70 newtons it was. That's what we got off the graph. So you know that this force here is going to be 70 newtons. And you could write it out as an equation. Force y times the sine of the angle, because we're looking at the component of that angle acting in the vertical direction, and that's got to be equal 70 newtons. We know that y is going to be equal in size, because otherwise it's not going to balance, so 70 over 70, which is 1, and if we inverse sine of 1, we'll get 90 degrees, providing you're calculating the right mode. So let's put those answers in. State and explain. So state, first of all, 90 degrees is going to be the angle. That's the first bit done. Explain, well, it needs to be equal in size, but opposite in direction. To achieve equilibrium, to balance that force. And then I might even do a diagram on the side to show what I mean by that. So we've got force Z here and force Y here. Question 3 tells us that the magnitude of x is increased to 160 newtons. We need to resolve forces, so it's going to be cosine and sine in there, to calculate the angle of theta. So let's go back and look at the question again, always good to refer back. So we now know that x is 160, so x goes like this. We know it's 160 newtons. We have z acting down, and we have force y acting at an angle of theta to the horizontal. Now another important thing to spot up in the question is that z is kept constant at 70 newtons. So we know that z is also 70 newtons. So let's see what's going on. I'm going to answer that over here. Now remember, the key idea is resolving this into its two components so that we can compare force y with force x and z. Now its two components are its horizontal component, shown in green, and that is right angles to its vertical component, which I'm going to show in yellow. Now remember, this is a really good trick in physics, is breaking vectors, in this case forces, into its two components so that we can solve problems. Because the great idea is that the horizontal component here is going to be equal to 160 newtons, i.e. force x, because those two have got to balance out to keep it in equilibrium. And we know that that is actually made up of y cosine theta. Why is that? Well, we know force y is there, and this is theta. We want to find this one here. If we then complete this triangle, that's a right angle there. This is the opposite, this is the hypotenuse, this is the adjacent. So we want to find the adjacent, we know the hypotenuse, so that's cosine theta is equal to the adjacent over the hypotenuse. The hypotenuse in this case is force y. Cosine theta equals a over y. Rearrange that, we get a equals cosine theta times y, which is that there. If we take the vertical component, we know that that's going to be equal to 70 newtons. And again, doing the same idea as we did up here, but doing it to try and find the opposite, we know that's going to be sine. So we know this is equal to y sine theta. So we can now got two really good little equations here. Y cosine theta equals 160, and y sine theta equals 70. Now we're going, right, we've got two unknowns here, we've got two equations, that's simultaneous equations. And the joy of this is, we know that also, and you expect to know this for CIE physics, that tan equals sine over cosine. If you don't believe me, try it on a calculator or Google it. So if we divide equation 1 by 2, we're going to get y sine theta equals 70 newtons divided by y cosine theta, and that's equal to 160 newtons. The y's are going to cancel, and sine divided by cosine equals tan. That's equal to 70 over 160. If we type that, if we type that into a calculator, tan theta equals 0.4375, and then to find theta, we inverse tan of 0.4375. You should get 23.6 degrees. Numbers were given to you to 2 sig figs probably, so I'm going to give that to 24 degrees there. So that's our working and answer for that question. Now we need to find the magnitude of force y. There's two ways we can do this. The first one is just using one of these equations. We could take 2 or 1, and knowing that we now know that theta equals 23.6. Keep the number in your calculator so you've got maximum precision. Not precision, sorry, I should say accuracy. Now, y is equal to 160 divided by cosine theta, if we rearrange equation 2. And then we just put our numbers in, cosine of 23.6. Again, make sure you use the full number that was in your calculator. And you should get a y value of about 175 newtons. So that goes in there. Just another way you could do this, remember we know that we've got 160 newtons of x going that way. We've got 70 newtons, of z going down. And then if we know the resultant y, remember it needs to close the triangle because it's in equilibrium, is that. If we put the right angle in, and I should have written 160 up there really, it makes it a bit clear. We want to find this one, which is the hypotenuse. We know the hypotenuse squared from Pythagoras is equal to the sum of the two other sides squared. If you solve that, you'll also get 175. Well, the next question tells you that the angle theta decreases as x increases. Explain why the object cannot be in equilibrium for theta equals 0. Let's return to our diagram up here. Remember that we're decreasing theta as x increases. Explain why the object cannot be in equilibrium at theta equals 0. So if we go back to here, you can see that we're asking why can this not be in equilibrium when theta equals 0. When theta equals 0, we're left with this situation here. We know that Z is always equal to 70 newtons, so that's not going anywhere. Now, the good news is X and Y can balance. That's fine, that can be in equilibrium. But the problem is Y is offering no component in the vertical direction to balance out this 70 newtons. So this can never be in equilibrium. If you want to try it, you just get a piece of string, hold one end here and one end here. If you apply any force here, you cannot stop this string bending. You can't keep it in equilibrium like this if any force is applied this way, unless you apply a force in the vertical direction. Because at the moment, if you're applying a force to keep this tight in the horizontal, then there's no component in the vertical direction. We need some of this acting in this direction to balance out the vertical component caused by Z. So, what they are looking for in this answer? Well, they just want the idea that there is no vertical component from Y or X, as a matter of fact, so that's completely horizontal, to balance the 70 Newton downwards from, what was it? It was Z, from Z. Okay, so there's no vertical component from Y or X to balance the 70 Newton downwards from Z, and that's what they'd be looking for in a question like that. Thanks for watching.